Hi, good evening, and it's 8 p.m. London time, and every week at approximately 8 p.m. we do a sort of live streaming. It's a video log and a podcast for our for news from Zimmer Peacock, and we've also started expanding it to also include some extra information for our ZP Developer Zone members. So let me jump straight into it because we've got an awful lot of material to, let's say, to cover this evening. So the first thing I'll do is just quickly scroll down. So this is the video log and podcast, but I just want to say that we've added some extra material in this evening because we've got some new members in the ZP Developer Zone, and there's been some specific questions. So I will address the questions first of all, and then go into the news from Zimmer Peacock. So as part of the ZP Developer Zone, we have a forum. And every Thursday at 8 a.m. London time, we do a specific webinar just for that forum. And then this week we've had 3 questions come up on the forum. Approximately something like Thursday or Friday this week, the questions came up, and I promised to give some answers. I mean, the questions themselves are quite simple. The questions were, do you have some data sheets for the nitrate sensor, the conductivity sensor, and the chloride sensor? And I will address that this evening because the answer is more complicated than it first seems. So let me just, as I say, there's 3 questions here. We're going to talk about 3 sensors, and then I'm really going to go and talk about news from Zimmer Peacock. So the first thing I want to say is I'm going to do on Thursday at 8 a.m. London time, when we do our webinar for the members, and any links that you see this evening, I will be putting them in the description later on, so you'll be able to find them. But this Thursday at 8 a.m. London time, we'll be doing quite a big webinar on metrics for biosensors, because when I get asked about a data sheet, it's kind of like opening a big can of worms, because the metrics around biosensors are so sort of complicated that I'm going to have to spend 30 minutes, even just skimming over the top of it. It's going to take me 30 minutes. But on Thursday, 8 a.m., that'll be the 17th of July, we'll do a bit of a Developer Zone webinar about metrics for biosensors. So please attend that if you can. Now I'll jump a bit more into this. What I am going to talk about on Thursday, I'm going to skip over it now very quickly. But on Thursday, then we're going to dig in a little bit deeper, because people ask us for data sheets for biosensors, and I think giving a data sheet on something like a temperature sensor or a pressure sensor, a sensor where the sensor is not in contact with the sample, or is very indirectly in contact with the sample, those kind of data sheets are fairly, let's say, straightforward. But what makes biosensors and their data sheets that much harder is you've got many elements that contribute the signal. You've got the biosensor, and you've got the biosensor sitting in the sample, and that's what makes it a really interesting, demanding thing, because you can do all the data sheets you like, and we do them in buffer. But of course, people are not running biosensors in buffers. They're running them in urine. They're running them in blood. They're running them on the breath vapor, as we do. Running them in plasma, running them in serum. So the question about, do you have a data sheet for a biosensor? The answer is, we have information about the sensor, but the best way of understanding the performance of a sensor is in a particular application, unfortunately, is to actually run it. But like I was saying, we do this webinar on Thursday, and then I'm going to cover in that webinar and discuss what range means in terms of biosensors, the limit of detection, what that means in terms of biosensors, the limit of quantification, and what that means in terms of biosensors. We're also going to talk about response time in terms of biosensors, because this would be the kind of information that people would expect in a biosensor. But of course, the response time of a sensor is proportional, for example, to the viscosity of a sensor. So if you're running it in urine, that's one thing. If you're running it in blood, that's another thing. So we'll discuss this, but we'll define response time of biosensors. We're also going to talk about settling time. Often you put a biosensor into a sample, and the signal takes a little while to equilibrate. So we need to discuss that in terms of biosensors. We also need to talk about, and this is an absolute classic, resolution of biosensors. We're always getting asked, what's the resolution of your biosensor? And the short answer is biosensors should be able to determine femtomolar and picomolar. But if you want to have that kind of resolution, you better have a really good experimental setup, and you better have a really good Faraday cage, and you better have a really good instrument. And sometimes people ask us about our resolution, and we almost have to ask back, what's the resolution of your electronics? So it's not always easy when people, ask you, what's the data sheet or what are the metrics around your biosensor? Because in fact, it's quite a nuanced answer. But I'll discuss this, like I say, on Thursday in the webinar there. And the other thing we want to talk about is manufacturing reproducibility. Simplicitly, in the simplest terms, when you make a series of biosensors, they can have variable offsets and they can have variable slopes. And people are always asking us, classic is kind of what's the accuracy of your biosensor? But the accuracy of the biosensor is really determined in how are you intending to use it? What is your application? So there's as many questions back. There are questions to a biosensor developer and a biosensor manufacturer like us. On Thursday, I'm also going to talk about the difference between specificity and selectivity. These terms are kind of used and synonymous with each other, but they are distinct. So some people ask us what's the selectivity, and some people ask us what's the specificity, and I just want to make sure we're all on the same page what we're meaning by these words. I also want to talk about sensitivity, specificity, precision, and accuracy in terms of a confusion matrix. And if you're not sure what a confusion matrix is, then definitely attend the webinar on Thursday. But this is really important, especially for those guys who are doing medical diagnostics. At the moment, Zimmer Peacock, we've developed this and it's being used in hospitals, a sensor for testing COVID-19 on the breath. It's a medical diagnostic, so it's very important to understand the accuracy of that sort of sensor. And when you're trying to diagnose a disease, sometimes it's not so important to have you really want to be able to give an answer. Does somebody have COVID-19, yes or no? That's almost like a digital response. Whereas in some applications, you actually want to know, what's the concentration of the particular analyte. So we're going to discuss that on Thursday as well. And we'll also discuss ROC curve, receiver operator characteristic. So if you're not sure what a ROC curve is, but you are interested in biosensors and sensors, then please attend on Thursday. So specifically now, we were asked about data and data sheets really about the nitrate sensor. There was nitrate sensor, chloride sensor, and osmolarity. So the first thing I'm going to talk about is the nitrate sensor. Now the nice thing about the nitrate sensor is the reason there's not too much of a data sheet up about it, and I will put these links in the description, these links, so just to remind me to put them up. What I'm going to talk about is a website that you might not be super aware of, called the ZP AgTech website. Now, the reason we don't have much of a data sheet on the nitrate sensor is we're not trying to sell it. We are actually trying to give it away. So what give it away, I mean it's free. But it's free with some clauses. So let's first of all talk about this nitrate sensor that we've had these inquiries about. So what's the problem? Why are we developing a nitrate sensor? And the problem that we're trying to solve at ZP AgTech is we have farmers and they are distributing nitrate upon the soil because they're essentially trying to get the nitrate into the plant so that they essentially get more biomass. Now the issue is that because there is no continuous monitoring nitrate sensor in the soil, the nitrate can actually be over applied, and it can end up running along the surface and getting into the water courses, or it can end up sinking down and getting into the aquifer. And either way, it's basically a source of pollution. And also, excess nitrate can just be broken down by the bacteria and end up going back into the atmosphere, and then it's essentially a waste. So we were asked, do you have a data sheet for the nitrate sensor? And I'm going to actually say, no, we don't. But it's actually because we're not trying to heavily sell it. But we are, and I'm going to talk about a beta program in a bit, trying to give it away and encourage people to use it. Talking about the nitrate sensor, but I just want to kind of talk about why this nitrate sensor's come about. So there's a nice guy at the John Innes Centre in the UK called Tony Miller, professor there, and he had invented some nitrate sensors because he was interested in measuring nitrate in farming or agronomy, and he, as I say, he's at the John Innes Centre, and this was his first prototypes. So yeah, I was talking to one of the Developer Zone members this morning, because what we're good at Zimmer and Peacock is taking academic ideas and quickly converting them into MVP, minimally viable product. It's such a shame, when research, goes really well and you get some data, but then it just stops. It doesn't make it to the market, and I think that's what's very different about Zimmer and Peacock. The reason people potentially should work with us or interact with us or collaborate with us is because we generally put technologies onto the market. So Tony's been developing a nitrate sensor for a few years, and he's been talking about it in academic meetings and showing these nitrate sensors in the soil. And I was lucky enough to attend one of these public lectures. I heard it, and I immediately contacted him and said, look, I'm very interested in this nitrate sensor. So he had a simple idea and we had a simple idea. Essentially, he's been making nitrate sensors out of pipette tips and earphone buds. And what he's been making really is his own version of a pH sensor. If you know anything about pH sensors, they're a form of open circuit potential sensors or potentiometry sensors, and another term for them would be ion selective electrodes. So he's essentially been making a form of pH sensor, but he's been making his specific to nitrate rather than acidity or basicity. And our simple idea was to actually convert that into something that was solid state. So one of the questions that I've been asked, and this is what I'm addressing, is tell us or give us a data sheet for your chloride, your conductivity sensor, and your nitrate sensor. And just out of interest, this is what they actually look like. They all look the same. And at Zimmer Peacock, we kind of understand that there's so many companies and so many groups, they develop these unique geometries and these unique sensors every time they want to do a new analyte. But the honest answer is you don't need to keep developing new electrode configurations or new geometries. I mean, this is what our nitrate sensor looks like. This is what our chloride sensor looks like. And this is what our conductivity sensor looks like. They're all the same. It's just the way we functionalize them or the way we excite the electrodes. But I've been asked to give or provide a data sheet for the nitrate sensor. I've just spent something like 50 minutes talking about the nitrate sensor, but I haven't provided the data sheet because we're not trying to sell it. But I am going to get to the point which is you can beta test this nitrate sensor, and we don't charge for it. So I just want to talk about where we are today with this particular technology. I think Zimmer Peacock is a very different company. We come to this developer zone every week, and we talk very strongly about biosensors and the science of biosensors. But actually, we're just as strong in our electromechanical engineering as well. This is an exploded view of a nitrate rod. So we've yes, just here, these are the nitrate sensors. So what you watched here is where we exploded the nitrate rod up, and so look at all the engineering that it goes in order to actually make what we call the nitrate rod. So what we've made here is we've made something that can actually go into the ground and deliver two sensors at a depth of 30 centimeters, or sorry, one sensor at 30 centimeters and another sensor at 60 centimeters. We're going live with this webinar, so Hasim just came on live online and said, "Well done to England," which is cool, because they won against Croatia in the European Cup this afternoon. But I just want to show, that these nitrate sensors, we've actually incorporated them into quite a lot of technology, which really reflects, well, we have great skill, let's say, in making biosensors and screen printed electrodes, but we also have great skill in the electromechanical and part of all of this as well. And this is where these nitrate rods, this is our engineers led by the project manager Niti, and you can see that we've got these rods, and these red zones indicate there's a little electrode here, and there's a little electrode there, and those are the nitrate sensors. So as I said, these rods go into the soil and deliver one nitrate sensor at 60 centimeters and another nitrate sensor at 30 centimeters. And then we have electronics, because these nitrate sensors are a form of ion selective electrodes, so they give out a voltage. So we have a set of electronics converting the electronics, for converting voltage into a protocol that's called SDI12. If you're not sure what SDI12 is, but you are interested in testing nitrate in water or testing nitrate in soil, then you probably have to become quite familiar with this protocol, because this is what the industry is actually using. And yeah, then we can connect to a weather station and transmit the data remotely, and all this is essentially done. So we have two products. If you want to be a beta tester with us, I'm going to show you a link in a bit where you can apply. And I'm going to tell you that the product that we're mostly giving out is this nitrate module. So you can see it's got essentially a solid state nitrate sensor highly embedded within this box. And then there's two cables with two wires, and you can read the voltage between those two wires. Let me dig in a bit deeper to this. As I say, you can measure the voltage between the two wires. And we've been actually taking these nitrate sensors, and in the first instance we were throwing them into the soil in the garden and burying them over and running them for several months. And now they've matured to a point where we're actually taking them into the farm, drilling a hole, dropping the rod into the hole, filling the hole back up, and leaving the sensors in situ. And we're able to run them off this little photovoltaic cell. So it's quite exciting. So the reason that we don't have much of a data sheet on this is because, in fact, we're not suggesting that anyone actually buys this. What we are suggesting is, if you're interested, I'll put a link under the video afterwards, and you'll be able to find that you can be a beta tester for this. And if you've got questions like, can I use this in other applications like water or hydroponics or something like that, take a look at the blog, and you should be able to kind of answer the questions by looking at the blog. So question number one, can you provide me with a data sheet for the nitrate sensor? The quick answer is no, because we're not encouraging you to buy it. We are encouraging you to click on the beta tester program, fill in the form, and apply to be a beta tester. And yeah, we really hope that you will become a beta tester. I stumbled for a second because the video is going live, and I think one of our really good guys called Saran, and you can see a picture of him in a bit, was just complimenting me on the photo, so I think he enjoyed the fact that I was in the field with a hat on earlier on. Cool. So yeah, please sign up as a beta tester. Then you can ask all the questions you want. You can talk to our engineers and you might enjoy the experience. The next question that came in is, can you give us a data sheet for the chloride sensor? So don't forget, on Thursday at 8 a.m. I'm going to do a big talk about metrics for biosensors and why it's such a complicated question. But let me try and give you some more information now about the chloride sensor. So the chloride sensor is a ion selective electrode. It's potentiometric. It's the same as a pH sensor, except rather than being specific, and Ahmet has asked a question online as well. Ahmet, specifically to your question, we're measuring open circuit potential. We're specifically just measuring the voltage between the two electrodes using a sort of essentially a very high impedance so that we don't get any flow of current. So it's technique, we would call it open circuit potential. You might just call it voltage reading or a potentiometer. It's really important not to allow current to flow. So back to the chloride sensor. This runs exactly the same way as the nitrate sensor. And this is the real beauty of electrochemistry. And the real beauty of electrochemistry is, I've just described a nitrate sensor and told you it was very similar to a pH sensor. And now I'm telling you about a chloride sensor. And by the way, it's very similar to the nitrate sensor and the pH sensor. And I'm just watching the chat online, and Hasim is just going, wow, it's actually in the soil. Yeah, Hasim, it's in the soil. I mean, this is, can you imagine how hard it is to make sensors that actually go in the soil and they have to operate for months on end? It's really demanding. And one of our ZP Developers Zone members, we do a lot of collaboration. One of them's in UK at the moment. He's going to get a joy of working on this project. So he should be hopefully very excited. So the chloride sensor, first part of the data sheet, let's say, is it's a voltage measurement. The next part of the data sheet, let's say, this is the sensor itself. There it is, small. We're measuring the voltage between two electrodes. Now it's quite unusual for us at Zimmer Peacock. We always make the working electrode the center electrode. In this case, we've actually moved it to be this pad here. So that is unusual for us. So this sensor has a pseudo reference electrode and a working electrode. And what we're doing is, in this chloride sensor, we're measuring the voltage between these two electrodes. Working electrode and reference electrode. And we're measuring the voltage between those two. If you want dimensions, they're here, because a data sheet would have dimensions. The length of this guy is 25.4 millimeters. Its width is 7 millimeters, and its thickness is 0.625 millimeters, and it's made out of ceramic. So ceramic is very inert, can withstand good high temperatures in itself, and these are the dimensions of the sensor. Now the next question in the data sheet would be, how do I connect to it? So you would connect to it using one of these connectors. We've got them on our website. And you would plug in here and here. So you need a potentiostat or some way of putting 3 millimeter banana plugs into those female ports, and that will allow you to make connection. I kind of show it like that because a lot of people have potentiostats. You don't, strictly speaking, need a potentiostat to measure an ion selective electrode. You just need a high impedance voltmeter. But for those in labs, they're often got potentiostats, so you need one of these connectors. We do have quite a lot of videos on our website, and there's one video on measuring a potassium sensor. I'm going to get really boring very quickly. A potassium sensor is an ion selective electrode, very similar to the nitrate sensor, except it's functionalized for potassium. So take a look at that video. Take a look at this video. This is the sodium sensor. Same thing, but functionalized for sodium. This is the pH sensor. Same thing, but functionalized for protons. This is the same thing. It's an ammonium sensor, but functionalized for ammonia. And I just want to sort of flash up those because, it's all very well us talking about this, but if you can physically see people running these kind of sensors, it can help you get a better grasp of what it is we've got. So take a look at those 4 videos. They might be useful. If you're struggling to understand when I start talking about ion selective electrodes and open circuit potential, I've not even mentioned the Nernst equation. If you're struggling, if you've not heard of this stuff, don't worry. Just sign up for the Academy, it's free. We've got a particular course up there called Module Techniques for Biosensor Developers, and you can read that for a couple, or not read it, there's videos and stuff, a couple of hours, and you'll be as good as any of us. The instrument that we use a lot on our website, I can see Armet's online, which is cool. I'm trying to encourage Armet to send me some data because I'm very interested in people doing open source potentiostats. But anyway, we sell potentiostats on our website. So you might ask, I'm coming slightly off on a tangent here, but why are we encouraging people to make open source? Sorry, that's when we sell potentiostats. Because we're a company that believes in disruption. You know, we want biosensors to be everywhere in our environment, in our healthcare sectors, you know, in our food production, because we want these sensors everywhere. We know that the electronics has got to be low cost, and the only way you can, one way of making the electronics low cost is to enable lots of people to be able to make them. Anyway, back to the point. When you watch those videos, we're using the Anapot, which is available on our website. I would also encourage you, if your budget's the Anapot is a very good potentiostat. If your budget's a little bit smaller, I would suggest the Senseit Smart, and you can measure these kind of ion selective electrodes using the Senseit Smart. We have a video about that on the website, and I'll send the link as well. So chloride electrode is an ion selective electrode. It's just like the nitrate sensor. You have to measure the voltage between 2 electrodes. You can use the Anapot potentiostat, or you can use the Senseit Smart potentiostat. And if you're using the Anapot, then you're going to have to use that connector that I showed. Osmolarity, that was one of the, that was the third electrode that was asked about as well. So the first thing just to say is we do have a very good video about osmolarity, osmolarity and conductivity and salinity. So I just want to kind of draw your attention to a particular video. I'm going to put these links in below as well, but these links will jump you straight into the videos where we do a demonstration. So we've got a couple of demonstrations online of how to make conductivity measurements using Zimmer and Peacock electrodes. So first of all, I want to say there are a few practicals that you can watch which will kind of help understand our settings. The instrument that we are using is the Anapot EIS. Unfortunately, when it comes to conductivity, it's harder when you're doing measurements like conductivity that I haven't yet got a kind of low cost option for, unfortunately, for you. So you'll need the potentiostat. It's about $6,000. You'll need the connector, and you will need some electrodes. Now the reason I bring this up is we used to make a big fuss about the electrode geometry that it was necessary for doing conductivity measurements. So we came up with this spiral configuration, but then we actually just some of our gold 303 electrodes, and we found out they work just as well. There's such a fuss in the world about making conductivity measurements, you know, that this is a Toledo probe. It will have 2 platinum electrodes that are exactly spaced facing each other, you know, and you'll make the measurement between them. And we've measured that Toledo probe, and we've measured against our spiral gold electrodes and our screen printed gold 303 electrodes. Gives the same data. Gives the same data. It doesn't matter if the electrodes are like this or they're in the same plane. Gives the same data. Doesn't even matter if it's in if the gold electrode's in a spiral or in a rectangle. Gives the same data. So to make a conductivity measurement, my first advice is going to be watch these 2 videos, 2 demonstrations by 2 of our guys doing them live in a webinar that we did last year. Then I'm going to say you're going to need the and a connector, and then we've done a lot of investigation over electrical configuration of materials. Makes no difference. So what you're going to need is what's called the Gold 303. This is on our website. That's the link to it. And in fact, that was the end of that bit. So that was 32 minutes. So the reason, and that's 32 minutes. I spent quite a long 10 minutes of it explaining that actually there's another webinar on Thursday that will complement this webinar. And I'll link to that as well, because then I'm going to talk about the complexity of metrics for biosensors. You know, a data sheet is a series of metrics that are meant to characterize that biosensor. But of course, biosensors are in contact with a sample. So how can you have a data sheet for a nitrate sensor when it could be used in water or in soil? The way it behaves in those two matrices is very different. And you're right, Hasim, it is very exciting that we got that nitrate sensor into the soil. So let me do a little change of pace here, or let me do a little change, and I'm going to change to the website. First of all, I want to hopefully that will hopefully that has updated. Yeah. So first of all, I want to thank Saran, who's online with us this evening. Saran is one of our very cool engineers, and joining us on his evening off is really appreciated. So thank you. So just is now the news from Zimmer Peacock for this week. So it's been busy. We've been having great fun. So the first thing I just want to talk about, some news from Zimmer Peacock, is this. A lot of the time in the webinars, we talk about bringing a sample to the sensor or putting a sample onto the sensor. What we don't talk about too much is we don't talk too much about flowing samples, but actually we are really interested in the pumping or the bringing of a sample to a sensor. So we put out a video this week. We'll link to it in this video. This is Anna, one of our engineers. She's obviously a fan of Queen, a rock band from the 80s and 90s in the UK. In this video, we describe a pump and we describe a flow cell. So it's a peristaltic pump, so it has tubing. The tubing gets squashed and it pumps solution. And I think this talks a little bit about Zimmer and Peacock, because the group that Saran is in, who's online tonight, also does a lot of mechanical work as well. And one of the things that they've done is they've manufactured a flow cell, so that we essentially have the pump and we flow through a flow cell, and it allows us to put sensors into the flow stream so that we can essentially sort of change the solution or bring sample to the sensor. So it's not something that we talk an awful lot about at Zimmer Peacock, but we're quite keen on flow stream. Well, we're quite keen on flow. So there it goes. So that's just some news from Zimmer Peacock this week. If you're interested, then I will put some links in down below.